Hi folks, this is the Unit 1 Day 4 lesson, and we're on the first video about multiplying a vector by a scalar. So in the last lesson we learned how to add and subtract vectors. Now we're going to look at multiplying. And it's really important to note that at this point we don't have a way of multiplying vectors. There's two operations that we're going to learn in Unit 2 that are sort of similar to a multiplication operation on vectors themselves. But in this unit, all we're going to be able to do is to multiply a vector by a scalar coefficient. So just to kind of remind you, a scalar is a number that has a magnitude but not a direction. So a scalar is any real number. So any of the real numbers that you've ever seen work as scalars for these operations. So when we multiply a vector by a scalar, so we'll use kind of a general vector u and a scalar k, it can affect both the magnitude and the direction of the vector. The direction, though, is kind of within some pretty limited constraints there. So depending on what the value of k is. And we're going to look through a number of different cases of what happens when we multiply a vector by that scalar k. So the first example we have is a train heading east, traveling at 120 kilometers per hour. So we want to draw vectors 1/3 u and negative u. So negative u we've seen, right? We've seen that negative vector or opposite vector. And we know that that's the vector that goes in this opposite direction and has the same magnitude. And I'm just going to kind of eyeball this a little bit, maybe a bit more. Pretend it's straighter than it is, and there's negative u. Now the 1/3 u, I think it's probably pretty intuitive that what we're going to be doing there is actually just multiplying the magnitude of u by 1/3. So a vector that's 1/3 u is the same direction as vector u, but just 1/3 as long. So I would keep it going in the same direction, going towards the east, and make it about 1/3 of the length in my diagram there. So that would be 1/3 u. So if we were to interpret that in terms of the train, this one, if u was here, then 1/3 of u has a magnitude of 1/3. So compared to the 120 kilometers per hour, this one would have 1/3 the magnitude. It's still traveling east, but it's traveling at 40 kilometers per hour. The negative u, so adding in this negative or -1 as a scalar, that changes the direction, but it doesn't change the magnitude. So the train is traveling now west instead of east, but at the same speed. So in general, we're going to kind of summarize what happens when we are multiplying vectors by these scalars. So here, the first case is if the k value, or if our scalar is positive, okay? If the k is positive, it doesn't change direction. So the new vector, k times u, will be in the same direction if it's positive, okay? And this is, a lot of kind of math and terminology, and but hopefully this makes sense. So the positive value means that it doesn't change direction, and it will have a magnitude of k times the original magnitude. Now, if k is a fraction, if k is a positive number between 0 and 1, the original vector will be shortened when you multiply it by a scalar. If k is a bigger number than 1, the original vector is lengthened, which obviously I think that makes sense, that say 1/2 u will be half the size, or 5u will be 5 times as long. So a bigger number than 1 will make it longer, and a smaller number than 1 for positive numbers between 0 and 1 will make it shorter, but all positive k values will not change the direction. Kind of the opposite of that is if we had a negative k value. So again, k is our scalar, u is a non-zero vector. If you have a zero vector, it doesn't matter what scalar you multiply it by, you're still just going to get the zero vector. Now, if we have a negative value for k, that's going to make the resulting vector after the multiplication will be in the opposite direction. So a negative sign for your scalar changes the direction of your original vector. So the magnitude, just to kind of note here, these absolute value signs, this is magnitude, and these same kind of signs that look like magnitude signs, if they're around a real number like that scalar, this is the absolute value, which you've probably seen before, and that just means that it's the positive value. So magnitude is always, always positive. There's no such thing as a negative magnitude. It would just change the direction. So magnitude is always positive. So here we have that the magnitude of the new vector is the absolute value, or just the positive part, just the number part, not that sign, times the original magnitude. So if we have a negative number that's a fractional number, so between 0 and -1, then this again will shorten it. A vector multiplied by a k value of, say, -1/2 will be shorter, but in the opposite direction. If the number is less than -1, so the numeric part is actually larger than 1, say like -10 or -5, those numbers would make it longer, but the negative part switches the direction. So basically, the sign of the scalar changes the direction, and the size or the magnitude of the scalar changes the magnitude of the vector, the new vector, when you multiply. I touched on this before, just kind of couple special cases. If you multiply any vector by 0, so if your k value is 0, you get the 0 vector. That's also true if you multiply the 0 vector by any scalar, you get the 0 vector still. Okay. We've talked about negative vectors. That would be a k value of -1, which means that you have the same value, same magnitude value, but the opposite direction. The last, I think we're on kind of the last definition part here, is about collinear vectors. So if vectors are collinear, it means that they're parallel. Remember that vectors have, I'm going to write this down again because it's so important. So vectors have magnitude and direction, but not location. So vectors are not situated in any particular location. They have a magnitude and they have a direction, but they don't have a location on the coordinate plane or in space. What they do have is magnitude and direction. So any vectors that are parallel to each other could also lie on the same line. It's not like in geometry or in looking at functions where you might have two lines that were parallel but they're not equal. If vectors are parallel, then you can say that they lie on the same line, because you could take, let's say this line here, I could have one vector over here and one vector a different magnitude, maybe different direction over there. And these vectors could both be picked up and placed onto that line. These vectors would be collinear because they are able to be placed on the same line. Vectors do not have a location. So these are called collinear because you can move them so that they would be on the same straight line. So collinear is really just another word for parallel when we're talking about vectors. We're going to use those interchangeably, but collinear is really the more accurate and more commonly used term. And this comes back to our friend from, I think, day 2, talking about this if and only if. So two vectors are collinear if and only if it's possible to find a non-zero scalar such that vector x equals k times vector u. So if we know vector x equals k times vector u, that necessarily means that these vectors are parallel or collinear. And remember our notation for that with the two parallel lines. But this is both directions is true. If we see two vectors that are parallel, we know that there must be a k value where you can take one vector and multiply it by a k value and get the other vector. That's true in both directions. Oh, one more definition part. Unit vectors. These should kind of give you a clue thinking about the unit circle. Remember, the unit circle is a circle with a radius of 1. A unit is kind of a single measurement. So a unit vector is going to be a vector that has a magnitude of 1. We write unit vectors with these, instead of a vector symbol, it's got those little hats on top, and we actually just call it U hat or V hat to indicate that it is a unit vector. So that little, I forget the name, but I'll see if I can look it up for you guys. That little notation with the hat shaped on top is how we indicate that a vector is a unit vector and has a magnitude of 1. So any vector with that kind of symbol there, so the magnitude of u hat equals 1. Unit vectors come really in handy when we're talking about scalar multiplication, because if we have a unit vector in a certain direction, we can get all of the other vectors in that direction by multiplying them by their magnitude. Kind of being able to multiply a vector with a magnitude of 1 to kind of stretch it out or scale it down to any other magnitude in that direction can be pretty convenient. And we'll see that more in the algebraic vectors. If you wanted to find a unit vector and you had a vector v, the way we would figure out a unit vector in the direction of v is, and this looks a little complicated, but it's to multiply the vector by 1 over the magnitude. So say, for instance, if the magnitude of v was 10, a unit vector in that direction, if we took 1/10 of this bigger vector, we would get a unit vector. Okay, so say, for instance, there's vector v. If we want to take 1/10 of that, I don't know what scale I'm measuring in here, could give v hat, which is 1/10 of v. It's the same direction, but scaled down to have 1 over the magnitude. So that's the formula for a unit vector, and that's why it works. You're going to take whatever the magnitude is and multiply by 1 over that magnitude to scale a vector down into a unit vector that would be smaller. I suppose, or bigger if you had, say for instance, a vector with a magnitude of 1/2, then 1/2 is 2, and then you could be stretching it up. Usually we kind of think about it as stretching those down, however. Okay, and I suppose pretty obviously if you wanted a unit vector in the opposite direction, you would do -1 over the magnitude of v and multiply it by the original vector.